Hello everyone, welcome back. In this video, we're going to talk about measuring the spread of data. So oftentimes when we're looking at a set of data, we're comparing certain values in that set of data to the mean or to the average. And a question that always comes up or is useful to look at is, how close is our data point to the actual mean or average? Sometimes just looking at the difference between a data value and the mean or the average, or the distance between a data point and the mean or the average, can be a little misleading. And the reason why looking solely at just the difference between a data value and the mean is that, well, sometimes the whole set of data can be clustered very closely around the mean or the average, or it can be more spread out about the mean or the average. And so I'm trying to visualize in this little illustration over here is we have two different distributions where the average and the data point we're looking at have the same distance apart from them. However, when we're looking at the whole set of data, we can see that in this first picture, this x value is a little bit more special because it's more uncommon for an x value to be that far away from the average. While in the second picture, there's a lot more x values that are that far away from the average. So while they're the same distance away from the average, this one isn't as uncommon as we see in the first picture. So looking at just the difference between these x values and these averages doesn't capture that behavior or that characteristic of the data. And so that's what we want to start building up next, is the way we measure that different spread of data. So we really want to talk about how the spreads of data are affecting the distances between our data values and the mean or the average. And the first concept in helping us kind of build up our tool here is defining this thing called the deviation, which is exactly that quantity that is the distance or difference between our data point and the mean or the average. And so the distance a data point is from the mean is called the deviation. And so our data point is going to be represented symbolically just by x, and our mean or average is going to be denoted as x over bar or x bar. And so the deviation is the distance or difference between our data point and the mean or average. So that's just the quantity x minus x bar. And if we were working with like a population as opposed to a sample, that might look like x minus mu instead of x minus x bar. And so we might think, well, we can kind of measure the spread of the data just by looking at the total sum of the deviations. And so to find the total sum of the deviations, we just add up x minus x bar for every single x value in our data set. However, this is actually not a very good way to do this. What ends up happening is if you just sum up the total deviations between data values and the average being found from the entire set or sample of those data values, well, you're always going to get a 0 as the sum of your total deviations. And that's always going to happen really just because of how that average or x bar is calculated in the first place, right? Some of our points will be above that average. Some of our points will be below that average. And so when we're just adding up the deviations, which can be positive or negative quantities, those positive values are going to cancel out with those negative values. And we always are going to get a total sum of 0 when we're looking at just the deviations. And so no matter how our data is spread out, if we calculate the average or the mean x bar and then look at the sum of total deviations, we're always getting 0. So that's not useful, but it doesn't mean we want to abandon this quantity that is the deviations. Instead, we might think, well, maybe we can make the deviations always positive so that negative positive interaction and cancellation doesn't occur. And that's a great idea. However, this alone is not all that is done in practice. So instead of just like throwing some absolute value bars around our total deviations, what we instead do is we square our deviations to make them positive. So by squaring the deviations before we add them up, it has the same effect of making them positive. So we no longer have that kind of cancellation between our deviations. And what's also really nice about squaring the deviations instead of just making them positive or taking the absolute value of them is that this rewards the x values that are closer to the mean or the average. And so if we have x values in our data set that are close to our mean or to our average x bar, then the difference between x and x bar is going to be small, like maybe 1 or 2. And well, if we square a number like 1 or 2, then we get a relatively small number like 1 or 4. And so we're adding up those 1 or 4 values when our x values are close or clustered tightly to the mean or the average. And so there's not like a lot of variance in our data. However, if we do have large variations in our data set, so x is far away from the average x bar, then those differences would be larger than like 1 or 2. The differences between our values and our averages or our mean might be like 5 or 10. Well, then if we square those differences or distances, squaring 5 or squaring 10 gives us 25 or 100. And that starts to really help us take into account how far those x values are from the average than just like looking at the absolute value of the deviations. So squaring the deviations makes them positive, and it also creates a little reward system for the x values that are closer to the average or the mean. And so if we sum up the squares of the deviation, it gives us this nice kind of way of adding up or looking at the total number of like squared distances between our data points and our average for that data set. However, that can sometimes be hard to work with on its own, especially if we're trying to compare different data sets against one another. Because what if one data set only has a sample size of 10, while another data set has a sample size of 100? Then we're adding up a lot more values in that data set that is a sample size 100 than we are in the data set that is a size of like 10. And so to help us kind of standardize this kind of sum of distances, or really sum of squares of distances, we're going to divide that total sum of the squares of the deviations by the population size. And when we do this, this gives us a quantity in statistics that we call the variance. So in general, the variance is found by taking the sums of the squares of the deviations and dividing by n the number of objects in your population. The idea is, with this calculation of the variance, if our data is tightly clustered together, we'll get a small variance when we compute this formula. And if our data is more spread out, then that'll show up numerically through a larger value of the variance. And so that quick little discussion is giving us a really informal derivation of this concept of the variance. But when we actually compute it in practice, we have to be a little bit more careful. We're always omitting some important details in algebra when we're talking through these intuitive derivations of these concepts or formulas. So we're going to have to be very careful when we calculate the variance for a set of data. It's going to depend on whether that data is representing the entire population or if it is just a sample or subset of the population. Okay, so we calculate the variance for a population or a sample slightly differently. It starts off in the same way in that we're looking at the sums of the squares of the deviations. And so our notation is really describing almost the same thing, but it's going to look a little bit different. So when we're working with populations of size capital N, the variance is denoted symbolically as lowercase sigma squared. And that's equal to the sum of all of our data values, x minus the average for the population, which is denoted by mu. So we just do a data value minus the average, square that, add them all up, and then divide by n the number of things in the population. And so when we're calculating the variance for a sample of a population where our sample size is little n, we denote the variance of the sample with little s squared, and the calculation is almost the same. We're still in the numerator summing up the squares of the deviations. So now the deviations are still the data values minus the averages. But remember, our sample average is denoted as x bar. The big difference in this formula, though, is we divide by n minus 1 instead of n. So for the population, you divide by capital N, the actual number of objects or data points in your total set or your total population. While when we're doing the variance calculation for a sample, we do not divide by the number of values in our sample. We always divide by one less. And there's some really interesting theoretical and algebraic reasons why we divide by one less, or n minus 1 instead of n. Without going too deep into all that algebra or theory, we want the variance for the sample to be a good estimation or estimator for the variance of the population. And what ends up happening is if you divide this by n instead of n minus 1, then the variance for our sample always ends up underestimating the actual variance for the population. So by dividing by the smaller number, that makes our variance of the sample a little bit bigger, which helps us alleviate that underestimating issue. It's a very easy mistake to make, so be careful and watch out for it. Make sure you're dividing by one less than your sample size instead of your actual sample size when you're calculating the variance of a sample. So the variance is this really important quantity that's like finding out kind of like the average of the total sums of like distances almost between our data and the mean or average for a set of data. However, these quantities that are the variance are not actual values that we could combine with our data values themselves. And if we think about the units involved in computing the variance, we can see why we cannot add or subtract one of these variance values to one of our data values. So our data values are like these x values. And just for the sake of clarity, let's suppose that x is representing like distance in feet. So x minus mu or x minus x bar is still measured in feet. However, when we square it, we're now multiplying a distance by another distance. And so that would have units of like feet squared. So we started with these x values talking about distances, but in this calculation for the variance, we're now talking about things that are like distances squared, like feet squared. So now we're talking about areas. And it doesn't make sense to add distances and areas together. Those units just don't mesh. So the way we can take a quantity like variance or area and manipulate it so that it can be added to one of our data values like a distance is by taking the square root of it, right? If you take the square root of area, you get back to distance. If you take the square root of feet squared, you get back to feet. So that is what we're going to do with these calculations for the variance of the population or the sample. We're going to take the square root of them, and then that'll give us a nice way of creating a standard deviation for the population or the sample. And so now we're ready to define the standard deviation, which is a critical concept in statistics. So we have two different types of standard deviations, just like we have two different types of variances. The population standard deviation is denoted as just sigma, and it's found by taking the square root of the population variance, right? So to go from sigma squared to sigma, we just take the square root of sigma squared. And so sigma, or our population standard deviation, is found by taking the square root of the sum of the squares of x minus mu divided by n, or another way to phrase that more conceptually, we take the sum of the squares of the deviations, divide that by the population size, and then take the square root of that number. And so our standard deviation formula for the sample is very similar. The same formula, just we divide by n minus 1 instead of n in our calculation. And it's still just the square root of the variance, but this time it's the square root of the sample variance, and it's denoted just by little s instead of s squared. And so the standard deviation along with the variance gives us some really useful tools for working with sets of data that are spread out in different ways. And now we have ways of measuring those different spreads of our data. Right, because the standard deviations are so closely related to these variances, we know that if we have a large standard deviation, then we also have a large variance and a larger spread of our data when compared to a set of data with a smaller standard deviation and a smaller variance. The standard deviations also give us a typical distance that a value may be from the mean or the average. So if we're comparing data values from two different sets of data, the values themselves might be very, very different looking. Right? One set of data may be working with money on the scale of like hundreds to thousands of dollars, while another set of data may be working with money on the scale of hundreds of thousands to millions or even billions of dollars. Right? $100,000 difference might be a big deal in one set of data, but not a big deal in the other set of data. And the standard deviation helps alleviate this issue of scales. So instead of talking about a data point being like $100,000 away from the other data point, we can talk in terms of standard deviations and say, well, that data point is only 1 or 2 standard deviations away from the mean or the average. And that gives us a sense of really how far it is away from the mean or the average when compared to another set of data and how far a data point is from that set's mean or average.